Hi, I'm Nir, and this is a joint work with Robert Krauthgamer and Sapir on the power of recursive embeddings for LP metrics. I'm going to discuss in this talk some sort of a technique which we call recursive metric embeddings or recursive metric reductions, which we applied for several problems on LP spaces. The problems are the construction of elliptic decomposition or a low diameter decomposition, nearest neighbor search, and the problem of constructing a low distortion embedding of finite point sets in LP into L2. I'm not going to discuss the construction of low distortion embeddings of finite point sets in LP into L2 in this talk. And also I want to note that for this problem, our results were actually improved by a software Kevin. Okay, so for the other problems, I'm going to demonstrate our technique on the problem of constructing elliptic decomposition. All our results are for LP spaces. I denote by LPD, just RD with the p-norm, where the p-norm of a vector is defined as usual. And we deal with the case when the value of p is greater than 2, and usually less than infinity. Okay, so let's discuss the problems and our results. So the first problem is the problem of nearest neighbor search. In this problem, we are given a metric space and a finite data set that lies in this metric space. And our goal is to design some sort of a data structure that, given a query point from the space, it quickly reports the closest point from the data set to it. So just to clarify, we of course know the data set in advance and have time to prepare, but we don't know the query in advance, so we have to prepare for all possible queries. For such a data structure, the performance measures are usually the query time, so how fast can we answer queries, and usually the best that we can hope for is something which is polylogarithmic in the number of points. And the space or pre-processing time, where we usually aim for something which is close to linear, so maybe n to the 1 plus epsilon or a small polynomial. And we considered also the case where we have an approximation factor c. So this is the approximated version of this problem. So instead of reporting the closest point to the query point, we are allowed to report a different point, this point z, as long as the distance between z and the query point is at most c times the distance between q and its closest point from the data set. Okay. So this problem is used a lot in practice, and we in this work consider the case where the metric space is LP, and when the value of p is greater than 2. So for this setting, there are actually many results. So I want to say just like the most relevant results to our work. So our data structure has a very fast query time, which is polylogarithmic in the number of points. So I'm just going to say results for this regime where the query time is polylogarithmic in the number of points. And in this regime, there are the two most relevant results are by Andoni and Bartal and Gottlieb. So the result of Andoni is something which depends on the number of points, and the results of Bartal and Gottlieb do not have these dependencies in the approximations. We have an exponential dependency in P and the approximation, and a polynomial space. So usually these results are stated with some dependency on the dimension, but for simplicity here, I'll just assume that the dimension is polylogarithmic at n. So for n and s, our result is that you can actually improve the approximation factor to being polynomial in P. But we have a space blowup, which causes the space to grow to something like n to the order of log p. Okay, and before we continue to the next problem and actually to see some solutions, I want to say that you can actually fix this space blowup or almost fix this space blowup, and also that we don't think that this is the end of the story. We actually think that you can improve the approximation factor further, as usually things in LP behave as some sort of an interpolation between L2 and L infinity, and this is what we get from interpolating the best data structure in these spaces. Okay, so let's move to the next problem, the problem of Lipschitz decomposition, which we'll focus on showing some solution for it today. So in this problem, introduced by Bartal, we have a metric space, and our goal is to decompose the metric space into clusters such that the diameter of every cluster is bounded by some value. Okay, and our goal is to do so such that every pair of close points fall in the same cluster of this decomposition. And when I say close, I of course mean when the distances are normalized somehow by the bounds of the diameter of the clusters. So clearly this is impossible deterministically, as sometimes we must separate pairs of close points because we have to draw the boundary somewhere. So to fix this, we introduce randomization and allow pairs of close points to fall in different clusters of the decomposition with some small probability. Okay, so a bit more formally, we say that a metric space admits a beta Lipschitz decomposition if for every target diameter delta, there exists a distribution over partitions of the metric space such that two properties hold. So the first one is that every cluster of the decomposition of this partition has diameter of at most delta, and this happens with probability 1. The second property is that for every pair of points, the probability that they get separated by the decomposition is at most their distance, normalized by delta, times beta. And usually, we think of the first term as being some sort of an ideal bound, as if the distance between the points is more than delta, they must be separated by this decomposition. So we can't have any guarantees regarding to the probability of separation. And the second term is some sort of a penalty which we wish to minimize. The general intuition is that close points fall in the same cluster of this decomposition with high probability. So we want to decompose the metric space into clusters of low diameter such that this property holds. Okay. Naturally, we wish to minimize the amount of penalty that we pay. So for a metric space, we define the decomposition parameter as just being the infimum over the betas, such that the metric space admits a beta Lipschitz decomposition. So this is just like what is the least amount of penalty that we need to pay in order to construct this decomposition. Finally, for a family of metric spaces, we define the decomposition parameter as just being the worst decomposition parameter for a metric space within this family. So these decompositions are very useful and they are used for many applications. So just to name a few, you can use them to construct geometric panels, distance labeling schemes, low distortion embeddings, and many other applications. And we actually know quite a few things about them. So also here, I'm only going to state results that are relevant to our work. The classical result is by Bartal, and is that for the family of finite metrics or endpoint metrics, the decomposition parameter is logarithmic in the number of points, and this is tight. And for LP spaces, we actually almost know the situation as well. So for the Euclidean case, we know that the decomposition parameter is the square root of the dimension, and for the endpoint metrics that lie in an Euclidean space, we know that the decomposition parameter is square root of log n. We also know the answer when the value of p is less than 2. And in this work, we actually resolve the problem for resolve this decomposition parameter for the family of endpoint metrics that lies in an LP space where the value of p is greater than 2. Okay, so recently we had some gap between what we knew for the construction and what we knew about the lower bound, and in this work, we close this gap. And we actually show that the decomposition parameter is almost the same as the decomposition parameter of the in the Euclidean case. So it is square root of log n up to a polynomial dependency in P. And I just want to note that also Naor and Ren got this work in parallel to us using a relatively similar technique. Okay, so this is the result that I'm going to show you. And I want to note that also that you can actually use this technique also to reproduce or almost reproduce Nor's result for LP spaces or for LPD itself when the value of P is greater than 2. Great. So let's move on to the solution. Okay. So in the solution, we'll actually try to reduce the problem from LP to L2, where we know how to construct good solution. And a general scheme to reduce problems in that deal with metric spaces is to use metric embedding theory. So suppose that we have some problem on a metric space. So think of your favorite problems, or maybe nearest neighbor search, or K-center, or Lipschitz decomposition. And suppose that we know how to construct good solutions for the problem in a different metric space. So for many problems, we know how to do to construct good solution in a Euclidean space as we understand the geometry better. So the general scheme will be to try to find some function that maps our metric space to the Euclidean space, or in general to some target space where we know to construct good solution, such that this mapping roughly preserves the distances. Okay, so the idea is that if we can find such a mapping, we can just solve the problem for the image of the point set, and then just map that solution back and get some approximated solution. Okay. And for LP spaces, maybe a natural candidate is the Euclidean space, as we understand the geometry of the Euclidean space better, so we know that many problems admit good solution in the Euclidean space. And we might think that maybe we can find such a function that like even exactly preserves the distances. And sadly, this is not the case. We actually know that we cannot embed finite points, even a finite point set in LP into a 2 without inducing some large distortion. So we need to have some additional guarantees in order to apply this reduction scheme. Okay, so the actual mapping that we are going to use is a mapping which is called the Mazo map. And it is a very simple mapping that maps LP to LQ. So for now, think of Q as being just L2, but I want to state it in the more general form as we'll actually use it later. So the mapping maps vectors in a very similar manner. It just raises every coordinate to the power of P over Q while keeping the original signs. So as for intuition, this mapping is very natural. As if you can think about it, if we think about it a bit, we see that this mapping maps the LP unit ball to the LQ unit ball. And actually, we'll use this property in our solution. You can show that if you have a set of some bounded diameter that lies in LP, you can shrink it to fit inside the LP unit ball, or shrink it and shift it. Apply this mapping and then scale things back, and we get that the distances roughly preserve when we apply this process, but the distance, how the distances are preserved depends on the bound that we know on the diameter in advance. Okay, so we can apply this scheme, this procedure if we know some bound and a diameter in advance, but if we don't, this procedure will be useless. Okay, so the general reduction scheme that we are actually going to apply is to take some set X that lies in LP such that the set X has some bounded diameter, and then we can apply the scheme with the Mazur map. So we map the set to LQ, and we know how to construct good solutions using the Mazur map, which will roughly preserve the distances. We'll solve the problem here, and then we'll map the solution back and get some approximated solution. And we'll see that we'll actually apply this process recursively to improve our solution again and again. Okay, so now back to the problem of Lipschitz decomposition. We'll actually see the solution. So just to remind you, we say that a metric space admits a beta Lipschitz decomposition if for every target diameter there exists a distribution over partitions of the metric space such that the diameter of the clusters is at most delta, and pairs of points get separated with probability at most their distance normalized by delta times beta. And the decomposition parameter of a metric space is just the least amount of penalty that we have to pay in order to construct this decomposition. Okay, so now to the actual solution or actual reduction. And we see that we can, for every endpoint metric that lies in LP, we can get the decomposition parameter to be something like square root of log n up to this polynomial dependency in the value of p. Okay, and this will be actually some sort of a reduction to the Euclidean case. So the square root of log n is no coincidence. Okay. So how do we do it? We wish to apply the scheme as we saw earlier, but we get some set X and we don't have any guarantees regarding to its diameter in advance. Okay, so we don't have any bound on the diameter. And suppose that we wish to construct this decomposition to some target diameter delta. The idea will be to use a two-step process in order to construct this decomposition. So in the first step, we'll actually construct an initial decomposition into a diameter bound which is slightly larger than delta, with some guarantee on the penalty. So we'll have some guarantee beta p on the penalty. And what we'll want to see is that we can actually improve the guarantee using this process. So we start with this some guarantee, and the idea is that we'll try to reduce the problem to sets of bounded diameter. So now we know that the clusters have bounded diameter, so we can actually apply the scheme that we saw earlier. Okay, so now for every cluster separately, we know that it has a bounded diameter, so we can apply the scheme that we saw earlier. We'll map it to LQ using the Mazur map, which will roughly preserve the distances. And then we'll construct a decomposition in the target space, and we'll use it to refine our original decomposition and get an improved decomposition, or maybe get the diameter bound back down to delta as we wished. Okay, so we do it for every cluster separately and refine the decomposition to have the guarantee that the diameter of every cluster is at most delta. So the final decomposition is just the combination of the blue and red lines. Okay, so this is the procedure that we are going to apply recursively. And what I want to show you is that we actually improve things, okay? What we actually showed in the paper is some sort of a lemma, which we call the bootstrapping lemma. And the lemma says that suppose that you have some set X, and you know that this set admits some initial decomposition, and suppose that you know how to construct solutions in LQ for every finite point set. So you can take these two decompositions. So in our paper, in this picture, this is like the combination of the blue and red lines. And you can use them to refine the original decomposition or get an improved decomposition for the set X. So you can get some decomposition with a parameter that depends on both of the decompositions. So the idea usually is that we think of beta Q as being less than beta P, and we're trying to improve beta P by applying this procedure. Okay, so we see that this new decomposition will have better guarantees than the original decomposition that we started with. Okay, so finally, how do we use this lemma to get our results? So we see that it is very simple. I'll show you a proof sketch. So we see that the decomposition parameter for a point set endpoints metric that lies in NP is at most poly P times square root of log n. Well, this is simply the decomposition parameter of endpoint metrics in L2. So this is some sort of a reduction that reduces problems in LP to L2. So the idea is to just apply the lemma recursively again and again, and where every time we improve the decomposition over the previous decomposition. So the final decomposition that we'll get, so this is not the actual proof, just like the intuition how to get it, it's just when we stop improving, so the fixed point of this procedure, we can find it by just plugging beta P equals beta nu. And when we do so, we get that this final decomposition parameter will be something like beta Q up to order 1 to the power P over Q. Okay, so to get just the results with exponential dependency on P, we just plug in Q equals 2, and we get that we can match this decomposition parameter of the set to what we know in L2. But we can actually improve further if we apply a second recursion over the values of P. So instead of like moving directly to L2, we use intermediate spaces in between. And we get that we reduce the decomposition parameter to being polynomial in P up to this polynomial in P instead of exponential in P. Okay, so this is the final solution or our main result. And I want to know that you can actually do it also for LPD, not just finite point sets in LP. And you can actually also match what we know in LPD to what we know in Euclidean space. And that's it. Thank you very much.